Okay, if you can get started. It's me again from yesterday, maybe you remember. And I'm going to talk about adding a performance monitoring support for KVM guests. And let's start by seeing what problem we are trying to solve. And that is, we want to allow users of virtual machines to be able to analyze performance problems that they have on guests in the same way, or perhaps even better if you can manage it, as they can on real hardware, on physical hardware. And there are many types of performance problems. Usually the most significant one is that you pick the wrong algorithm, and it takes a lot more time than you could do by picking another algorithm. There are networking problems. You can have problems with your storage. Going closer to the CPU, you can have a bad usage of the cache or the TLB. There are a lot of SMP and NUMA issues, particularly these days where all machines are very parallel and NUMA is very popular. You can have issues with your language runtime if you strayed away from C. You can have problems with your scheduler. And if you're doing virtualization, then virtualization can introduce its own set of problems. Now, most of these, or some of these, can be solved by, analyzed and solved by tools that exist in the guest in the same way as they are in the host. For example, you can use VMstat to see your, to analyze your block I/O and block trace if you're running on Linux to see exactly what patterns of I/O you have. And for the most part, it works very well. One part that is missing currently from KVM is the ability to use the CPU's performance monitor to detect issues that are close to the CPU. Things like cache and TLB and actual CPU cycles used. So hardware has, modern hardware has a performance monitoring unit that is a very advanced set of tools that can be used to monitor and analyze performance issues with the CPUs. So what it is a set of counters that keep counting each time a specific event occurs, and these events are programmable. There are generally two types of events. The first of them is architectural events. Those are events that are correlate one-to-one with the instruction set. For example, when an instruction is executed, then that can count as an event, and it has a one-to-one correlation with your binary code. The second type of events are microarchitectural, and those are not related one-to-one to your source to your object code, but are more related to things that happen inside the CPU. For example, modern CPUs can crack instructions into several microarchitectural instructions. And if you count these instructions, or certain types of these instructions, then these no longer correspond one-to-one with your object code. And they vary from processor implementation to processor implementation. And an example of a microarchitectural event is this memload uops retard hit LFB, which looks like it has been written by a lawyer. This is an example from the actual manual. So some people can actually understand this, but there are pretty few. And there exist tools that can program these counters and read them afterwards and correlate them with your source code. So you can have a nice display of which line of source code is taking a long time to execute, or perhaps which lines of code incur a lot of cache misses, and so they slow down your program. So the x86 has a very extensive PMU, very capable, but it comes with a few issues, especially related to virtualization. Now, one of them is that it's very vendor-specific. So the PMU on an Intel host is very different from the PMU on an AMD host. And it's even very model-specific. So the PMU on the Intel host you bought yesterday is very different from the PMU on the Intel host that he bought a year or two ago. And that is very virtualization unfriendly. We try to abstract away differences between hosts. So if you have different network cards, you don't present them as different network cards to the guest. You abstract them as a single VirtIO card. And this is pretty bad for virtualization. It's also a limited resource. So you typically have only a small number of counters, like 3 or 4. And you can program these counters. You can have each one program something different. But you can't count all of the events simultaneously. So you need some kind of way to schedule. If you have multiple guests counting different things, you need some way to share this limited resource among the guests and perhaps among the host. And also, it's pretty slow to program. On the x86, the PMU is programmed by something called model-specific registers. And those are relatively slow instructions that are used to program them. So if your PMU tool is slow, then you're introducing performance problems instead of monitoring them. So this has been realized by the vendors. And there is now something that is called the architectural PMU. Architectural in this context means that it is part of the instruction set. And therefore, it is stable and will not change, or at least it will only change in a compatible way among different revisions of the CPU. So the architectural PMU doesn't have all of the capabilities of the model-specific PMU. Of course, it cannot do any of the microarchitectural events, because these do change from processor family to processor family. So all of these events will be architectural events. The program interface is fixed. It doesn't change from version to version. So you program it through something called the architectural MSR. And if you recall, MSR means model-specific, and architectural means non-model specifics. So these are non-model-specific, model-specific registers. Probably the same lawyer from the previous slide wrote this. And it's stable across processor revisions. So they actually revamp the specification so you can gain more capabilities. But once a capability is introduced, it's not going to be removed. You can count on it. So a program that depends on an architectural PMU feature will continue to work on newer processors, unlike the non-architectural PMU. Something very important about the architectural PMU is that you can discover it via CPU ID. So it means that if you expose it to the guest via the CPU ID instruction, then the guest can discover it and know exactly what features are available, unlike the non-architectural PMU, where the guest just looked at the CPU model that it's running on and inferred from that all of the features that were available. So this is very good for virtualization, because we do a large part of it is exposing things via CPU ID. And unfortunately, it's Intel only. AMD has not picked up on the specification, but maybe as time goes by, they will, and we will have a truly cross-platform PMU. So let's look at the choices that we have when choosing to implement a PMU for a KVM. And let's look at them briefly. Let's start with a point of view. So the two choices are, the first of them is to do everything from the point of view of the host. You run your performance monitoring tool on the host. And this has a few advantages. So first of all, you can see the entire system. If you have multiple guests they may be interfering with one another, from the host point of view, you can see that and take action. Or maybe they can be host processes or the kernel on the host. You have a global view of the system, and that has a lot of advantages. And also, you can see the problems that virtualization itself induces, because you run it from underneath the virtualization layer or from inside the virtualization layer. And so you can see the effects that it is having. The other side of that choice is do things from the guest point of view. And that also has a number of advantages. So the first advantage is that all of the existing tools and the mindset people are used to working with the performance monitoring tools on physical host. So if you're running the same tools from inside the guest or similar tools, then you already know how to work with them, and you can reuse your experience. Also, you integrate your PMU tools with the guest operating system and processes. So if your tools can associate an event with a specific process, then you retain that capability. That is a lot harder to do from the host because, well, the host can see a guest kernel, but it's very difficult to reach out and see the actual user processes inside the guest. That's too many levels of interaction. Another thing that's important, very important for KVM is like cloud deployment. In a cloud, the host and the guest are owned by different people. So you rent your guest from a cloud provider, and they don't give you typically access to the host. It's their host and your guest. And if it's a private cloud, the situation is probably worse because it's people from the same company in different departments. They probably would never talk to each other. And of course, live migration. If you're running things from the host and you have a large management tool that's responsible for load balancing guests across your cluster, then you can be monitoring your performance problem, and then your performance problem is live migrated away into a different host, and you're left looking at nothing. Whereas if you have the performance monitoring tool running inside the guest, then it's migrated along with the guest that you're monitoring. So that's really important for clouds or for large consolidation scenarios. So I would say that the host point of view is really good for developers who are especially developers of the virtualization layer itself, while the guest point of view is more for the end users, which are also developers, but developers of the end user application and not of the virtualization system. So just to remind ourselves, this is the first choice on our list of choices. So suppose we So suppose we take the guest point of view, and again we have a choice to make. Whether we assign the host PMU to the guest, or whether we virtualize it. So if we do a pass-through of the performance monitoring unit, that is, we allow the guest to program the host PMU directly, then we get a number of advantages. The first of them is that it's really fast because we don't have to virtualize all of those instructions that read and write those MSRs, those model-specific registers. So it's a lot faster than a virtualized PMU. And it's accurate because virtualization introduces latencies. And if you started to do scheduling and things like that, we will see it later, then you lose accuracy. So if you just give the guest direct access to the host PMU, then you get the best accuracy, which is important in many scenarios. On the other hand, the virtual PMU has, virtualizing the PMU has its own advantages. Probably the most important is that it's secure. The problem with assigning a PMU is that some of the events are not specific to the core or thread that you're running on. So they may be delivering events from the entire socket, from the entire package, or they may be delivering events from the entire core, which may be running more than one thread. So you can be gaining information through the use of the PMU from threads that do not belong to the same guest you're running on. And that may be a danger in certain scenarios. There are lots of stories running around about how you can detect SSH keys just by looking at cache events. And we don't want this source of information to be available to guests. So this can be mitigated, for example, by scheduling all of the threads of one guest on a single core, or if you're talking about package-level events, scheduling all of the threads, all of the vCPUs of one guest on a socket. But of course, it has its own set of problems. If we virtualize the PMU, it's also shareable. Because we don't give the guest direct access to the PMU, we can have multiple users of the PMU running in parallel, each of them utilizing a subset of the counters that are available, perhaps multiplexed in time. And that's important when you may have potentially someone running a performance monitoring application in the guest, and at the same time, someone running a performance monitoring application in the host. And it's really important from the Linux point of view to be able to share resources. That's actually the job of the kernel, to multiplex access to resources. Assignment, like we have in device assignment, is an important option, but we usually prefer to virtualize. And another advantage of the virtual PMU is that we don't have to, but we can choose to make it model independent, so that it doesn't change when you change your host, perhaps through live migration or just because you upgrade your host. Typically, users of virtualization expect their hardware not to change when something happens to the infrastructure. They expect their hardware not to change. That's one of the primary advantages of virtualization. So we would like not to break it. So let's move back to the choices slide. So that's the second choice that we have. And by the way, I'm not giving any hints about the meaning of the colors for the bottom 4 boxes. OK, so the final choice that we have, provided that we choose to virtualize a PMU, is what type of interface this PMU has. So one choice that is popular in certain other virtualization solutions is to pair-virtualize. And that has the usual the usual advantages. It's very flexible. You can do anything you like. And it's also it can be very fast because you can architect it in a way that minimizes the amount of host-to-guest transitions. And because you have full control, it's pretty easy to make it a lot faster. The other option is to go with the architectural route, to pick up the specification of how the hardware does it and just follow it. And that really has a good advantage. You have a specification, so you don't have to write one. Writing a spec is pretty hard. Actually following the specs that you write is sometimes even harder. Also making sure that it's a good spec and survives for multiple years. It's also compatible with guest software. So if you have software that was written to the same spec, then that software can keep on working. You don't have to modify it to work with your vPMU. And something else that we've already seen several times in KVM is that it's compatible with future hardware improvements. So if the processor vendors decide to add support for virtualizing the PMU, then we can just remove our code that does all of the virtualization, and the same interface exists to the guest without any change. Whereas if you're doing a pair-virtual PMU, then you're faced with a new choice. One of them is to keep on with your pair-virtual PMU interface, which the software is working with. But then it becomes slower than the hardware, because the hardware now does all of it in hardware. And on the other hand, you can tell your users, OK, we're dropping the pair-virtual PMU. Go back to the architectural PMU, and they will love you for it. And we've seen that in KVM. We had support for pair-virtual MMU operations. And we later pulled them out because they turned out to be a lot slower when modern hardware came out. So usually the choice in KVM land is to go with the architected way and try not to be too clever. So that shows a complete matrix of choices that we can make. So let's look at what Linux offers us in the way of infrastructure. Of course, the main reasoning behind KVM was to reuse everything we can from the Linux kernel infrastructure. And in this case, it's no different. Linux Perf events is the interface to the PMU. It was added relatively recently by Ingo Molnar and his gang. And it really treats the PMU like any other hardware resource. Like you have a network card driver that virtualizes the NIC and makes it available to multiple applications simultaneously and in a secure manner. In the same way, Perf events takes the PMU and multiplexes it and makes it available to multiple applications within the host. So it does this by scheduling the counters. If you oversubscribe your PMU, if you're asking for more counters than the PMU actually provides, then Perf events will timeshare those counters across the request and fulfill your requirements. So it can do host-wide counters. You could ask for events on any CPU, on all CPUs, or on a specific CPU. And you can have process-specific counters that are attached to a specific process. And as a process will be migrated across CPUs, the Perf events will deprogram the PMU on the host that you're migrating from, and then reprogram it on the CPU you're migrating from, and reprogram it on the CPU you're migrating to, and do all of the internal accountings, and everything works out without any effort on the application's part. It just works. It also provides software counters, so you can count things like page faults and context switches and lots of other events that can happen to a process in its lifetime. And of course, the PMU counters, and it supports both a set of generic counters that are available on all types of CPUs, and also model-specific counters that you have to know exactly what CPU you're running on and prepare for that. And actually, Perf events supports a lot more than that. It's a very capable subsystem with a lot of features, but not all of them are relevant to the PMU. So let's look at the Perf KVM, and that corresponds to the leftmost choice on the slide. If you go from the host point of view, as we said, it's most useful for developers of the virtualization system. They can get an overview of everything that is happening, both in the guest and on the host and the virtualization layer itself. And this is very useful for developers. So this was merged, I think it was a couple of years ago, and it's called Perf KVM, the Perf tool that comes with the Linux kernel. And what it does, it just extends the Perf tool to record not just events that come from the host, but also events that come from the guest. And it is able to reach into the guest and pull out the debug symbols. And so you can see not just raw instruction pointer values, but also you can correlate them to source lines of code, and you can see exactly where your problems are. Of course, it's somewhat limited. It cannot reach into a guest user space, just a guest kernel, but in many situations, it is sufficient. So let's look at the other side of the problem, and that is the virtual PMU. And in KVM tradition, we chose to implement the architectural PMU and not pair-virtualize it, at least not for now. So let's look at what Perf event provides us for the architectural PMU. As it happens, the events that Perf events provides correspond exactly to the events that are provided by the architectural PMU. It's a really lucky coincidence for us, because that means that we don't need to do any model-specific programming when we virtualize those events. If a guest asks us for the counter of instructions retired, then we just ask Perf events for a counter that provides instructions retired, and we pass that value to the guest. There are a few details that don't match exactly, mainly because there has been no real requirement from them for perf events, and also because they are not available across all CPUs. An example is CMask. I think it's called the counter mask. What it means that if it only counts if only if a certain number of events happen simultaneously in the same cycle. So you can use it, for example, to see if you can dispatch or retire 2 or more instructions per cycle, or even more. And that's useful sometimes to see how good the CPU is in utilizing its full width. Current CPUs are very wide. They can execute multiple instructions simultaneously. And you can see if you're utilizing those capabilities. So this particular capability and a couple of others are not exposed, but they're not really that important. We can live without them. So how do we use perf events to emulate a virtual PMU? So what we do is we detect the guest writes to the PMU MSRs. We intercept them. And we infer what the guest is trying to do. So we try to see which counter it's programming and what type of event it is monitoring and all of the various options. And then we just program, we ask the perf core to program those same events. And it will program the host MSRs. And typically, it will be very similar values to what the guest asked if we happen to run on a similar CPU, on a CPU that supports the architecture PMU. But it may be a very different programming if we're running on a different CPU. And everything else will be done by perf. It will take care to migrate the PMU counters from one CPU to another if our virtual CPU is migrated. And it will, if there is a request for counters on the host itself, then perf will take care to multiplex the 2 different requests in time so that all of them can be fulfilled. OK, so there are a few problems with this approach. And the first one is probably the biggest, and that is very few applications actually talk to the architecture PMU. One reason is that it's relatively new, so perhaps the application did not have enough time to adopt. It's also less capable than the model-specific PMU, and many of those performance monitoring applications try to do everything, and so they try to go for the most amount of information. So we will need to test and to qualify, perhaps modify some of those applications, which somewhat defeats the purpose of using the architectural PMU, but at least we have a spec to follow. Another issue is that visual PMU is quite slow. It takes multiple MSRs to program an event, and each of them has to be intercepted by KVM and forwarded to perf, which then also issues multiple MSRs to program the actual hardware. We may be able to mitigate some of that by using the next revision of the architectural PMU, which has a faster programming model. So you can use less MSR writes to program your PMU. A single write can enable multiple registers and multiple counters. And that makes things somewhat faster. A third problem is that Linux, which is from our point of view, it's a primary tool that is running in the guest, Linux itself. It will not try to detect the architectural PMU on AMD host, simply because it was not available until this time. So we will have to patch it probably to look, since it's available via CPU ID, it's pretty easy to look for the specific CPU ID leaf, and if it's there, we can use it. So what remains to be done with the PMU? We need to test and merge it. The code is ready. It has been posted on the mailing list a couple of times. There are reports of problems where the vPMU causes slowdown in the programs that it monitors. It's really not what we're trying to do here. We're trying to monitor the programs, not slow them down. So we'll have to understand that problem and fix it. Currently, we implement version 1 of the architectural PMU, which is not as capable as the next revisions. So I plan to take a look at implementing those next revisions and offering them selectively based on user requirements. And if it turns out that it's still slow, then we may have to do pervert acceleration, despite the fact that we try not to do it usually. So it really depends on testing results and on requirements. So this is it. Any questions?